Hello, this is part 3 of my Roger Klang's Actual Philosophy from my book Causation and the Universe, a bridge between the 1900s and the 2000s. We have to revise the semantics in certain suggested variants of formulas for Gödel's incompleteness theorem and Plato's theorem, but Edmund L. Gettier's theorem remains a shining example still. A suggested variant of formula for Gödel's incompleteness theorem. In any logical system for mathematics, there are statements of speech that are true, but that cannot be proved. This statement cannot be true, must be either true or false. If the claim is false, it can be proved. Then it must be true, which is a contradiction. Therefore, the claim is true. This is therefore a mathematical claim that is true but cannot be proven. The mathematical implication is, what if the Riemann hypothesis would prove to be true, but is impossible to prove? Well, it seems to me this suggested variant of formula for Gödel's incompleteness theorem gets entangled in its own linguistics. It is certainly a logical argument based on the theorem, but you cannot use the order in which the words follow mathematically. What do I mean? Well, the sentence, "This statement cannot be true," must indeed be either false or true. But if it is true, then you should, if it is possible to translate it into a mathematical formula that says something about something other than linguistics, replace the words "cannot be true" with the words "is not true," which makes it correct without the inconsistencies. Y can stand for "is not true," and X can represent "must be true." A can stand for the opening words "this statement." The theorem as it appears above the asterisk proves that it linguistically can be either false or true, though it cannot be proven. But does it prove anything with mathematics of the nature of the world beyond it? No, it rather seems to disprove the theorem itself. The theorem doesn't help us understand the world. Perhaps one cannot conclude a solution from the first "this statement" or A with both "must be true" and "cannot be true" for it to be a correct formula. Either "this statement" or A is true, or it's not true. So why should read "is not true" if it should be adjacent with "this statement" or A, since "can" is a statement that says that something either is or is not, but not both at the same time. When you put "not" after "can," "cannot," you're either saying can, as in must or plus, not minus equals minus equals is not true, which translates into a mathematical language plus and minus equals minus, or with other words, it is a negative. Or you are saying can, as in not minus equals plus equals must be true, which mathematically translates into minus and minus equals plus, or with other words, it is a positive and henceforth must be true. Conclusion: is not true or cannot be true is a correct wording, but not cannot be true. And what is the statement A? We don't know. What we are doing is to apply the label of an unknown statement to a formula. But we cannot say anything about any actual statement. Is that logical? Surely, this statement A is not a statement. So what we have got left in Y is A is not true, or A is false, plus minus equals minus, or just plain minus. Maybe we need to accept the fact that the answer to the Riemann hypothesis involves no pattern in any sequence of prime numbers, and still the enigma could be solvable if we look outside the box. The image with the text, the next sentence is true and the previous sentence is false, is an anomaly if you translate it into a mathematical language. Think about how wrong it is linguistically to not say anything about the sentence we read for the moment being, but instead say something about the second sentence, which we do not read for the moment, and haven't had the opportunity to infer anything from now. The sentence we are reading does not in any way entail the other sentence, but is merely referring to it. These two combined sentences in the above image with the dinosaur are related to the first suggested formula on Gödel's incompleteness theorem. This statement cannot be true, but only separated into two individual sentences, and without the inconsistencies that comes with the word or words cannot, can as in must, plus, alt, can as in not, minus, plus not, minus. From the bipolar word can and not, which the originator didn't split up like I did here. The above statement in the image is like saying x plus 1 equals something in another formula, the next sentence. Here not specified or even correlating with the next sentence. It translates into the next sentence x is true, 1, and then goes on to saying the previous sentence y is false, minus 1. The two sentences are simply not translatable into any logical algorithm one can solve. It only states that x equals 1 and y equals minus 1. Or maybe you should say that x equals minus 1 and y equals 1. But it still does not translate into any logical algorithm with a plausible answer. There is no mathematical connection between the two sentences. Not even an equal sign. It is like saying the next bun, X, is tasty, 1, and the previous bun, Y, is disgusting, -1. You could also shift the meaning in the two statements, the next sentence and the previous sentence, and get this sentence Y is true, 1, and this sentence X is false, -1. This sentence is true is always a true sentence. This sentence is false. If it is a true statement, it must be false. If it is a false statement, it must be true. It's a pun that is transferable into a solvable mathematical formula, x equals -1. Thus, x is false, and when one reads it in its mathematical formula, one can see no further implications, because x equals -1. It shows that there can be something illogical and subjective with the linguistics we humans use.